guys are going to walk through Where'd you go? Walker.
Hello, afternoon. I'm Keith Summers from Productivity Quality. Thanks for coming to the seminar. We've got a couple of presenters today, Tony Patillo from Mitutoyo and Adam Clark from PQI. And Tony is a veteran at this. We do some kind of a surface-informed seminar each year. Last year not included due to their COVID restrictions, but we're back on the program again. And so Tony is going to present the basics end of things, talking about some of the 2D surface metrology aspects, and then Adam is going to come in following Tony to talk about some of the 3D kinds of things. So Tony's going to look at more of a stylus-based approach where we're making contact. Adam is going to talk about non-contact surface metrology, where we can look at things like aerial parameters, but also just general surface metrology kinds of things, waviness, even some things as far as some geometry measurements. All this stuff is back in our area in the far corner there, so please feel free afterwards, come by and see things live and in person. So, Tony, thank you.
Thank you, Keith. Make sure that's not too loud. Good afternoon, everyone. We have a lot of technical information here because the measurement of surface roughness is a very common measurement that's needed, but it's a very complex science in itself. So I'm not going to sit and read all this. That has a lot of big words and it's very technical, but I'm going to talk about tactile 2D roughness testing with a diamond stylus. And before we get into this, it's very important because most of these types of components that we're measuring for surface finish, it has a mating surface and it's critical that it functions properly. And this is the very micro level of things. The very tiny peaks, valleys, and deviations of a surface can have a great impact on how something seals or mates with another part and functions for the life of the assembly. So I may go through some things very quickly, but I'll very much focus on the important things here. So, as we look at a part from a macro level, I had one. The primary features of a surface are, on a macro level, the size, position. Then we get into this world to some degree with form. Now we get into the actual texture of the surface. There's a lot going on there, although we primarily look at the roughness. But there are larger components like waviness. But that smallest level that we're looking at, those very fine peaks and valleys of that surface that can have a high impact on its function, it's roughness, and that's what we're going to talk about here today. Why do we measure surface roughness? Hey, I have to measure it because it's on the print. I need to make sure that it complies. Identify good and bad parts. But like most of metrology, we can use this information and control our process and adjust things before we have bad parts or defects. This may be hard to see, but this is a nice chart. Different types of machining and ways that we make parts produce a different surface finish. You have everything from saws that will have a very coarse surface after you cut it. We're more down in the world down here where we have, sorry, I can't see it. Other side. Down here where we have grinding, finishing, honing, things of that nature, where we have a smoother finish that we want to check with this type of equipment. It's a complex science in itself, but the nice thing is there's a long history of tactile roughness testing, and there are many standards that have defined a lot of the ranges and parameters and settings and the ways you go about taking these measurements. So a lot of this presentation, I'm going to refer to some of these definitions. At the core of tactile roughness testing is the detector, the sensor that is holding the diamond stylus and monitoring as it traverses across, measuring those peaks and valleys. And inside of all of these tactile sensors is an LVDT. It is very good. It has very fine resolution. It can see very small changes over a very narrow area. Most of these sensors have a total vertical travel of 32 thousandths of an inch, or 0.8 millimeters. So we're not traveling an inch up and down. We're looking at those micro peaks and valleys, and this sensor is capable of nanometer resolution across that very small range, utilizing an LVDT. The core system on any profilometer surface roughness analyzer, we need the detector itself, which we just discussed, the LVDT, which has a diamond stylus, some type of drive unit to pull it across in the x-axis, and some type of analyzer to take that signal and create, typically now, the digital data points we want in a software or a firmware and produce the results that we're after. There are many different types here. You guys have probably seen small handheld units, something you can hold in the palm of your hand, and there are systems that are fully automated with 5 or 6 different axes to maneuver parts around, but the core is always there. We need that detector that can sense those small peaks and valleys. We need something to pull in X, and we need something to analyze it. It's very important in tactile roughness testing to understand the benefits and limitations of the 2 different types of tactile roughness testers. This is what we call a skid measuring type. The skid refers to the bottom part of that detector actually has a skid or a face on the bottom that has a hole in it that the diamond protrudes through. That entire skid is pressed against the surface with a significant amount of force, making this a more rigid test, something a little more conducive to an environment that's not completely free of vibration and other issues. So that entire skid is pressed against the surface, the X is pulling, and then independent, that diamond stylus is monitoring those peaks and valleys as it pulls across. As this shows, the skid type system, you have a skid datum, that's that face that's being pushed by the pivot with a large amount of force against the surface, making it more rigid. And then the diamond stylus itself has a very low amount of force and is monitoring the peaks and valleys as it gets pulled across. This one is the most commonly used system because it's very compact. It's more protected. That skid nose piece protects the stylus to some degree. They're the least expensive and the most commonly used. But there are limitations to this type of system. One limitation is because of the mechanics of that skid following the larger components of the profile and only measuring with the diamond the smaller components, you can only measure roughness with the skid type system. We'll talk in a moment. There are some other components to the surface that sometimes we want to monitor, such as waviness, that is mechanically filtered out if you're using a skid type system. But most of us are after roughness. A skidless system, as the name implies, gets rid of that skid. Now, as you'll see, I knew that might happen. As the name implies, no more skid being pressed against the surface. Now only the diamond tip of the stylus is in contact with the surface. So this is measuring that true profile with no mechanical filter. The benefit here is if you could perfectly measure in the same place with the 2 types of systems, skid and skidless. Since this is free of any type of mechanical filter, this would always be the best representation of that real surface because only the diamond is touching and monitoring those peaks and valleys. There are a lot of benefits to this. It's, as I mentioned, a truer representation of that surface. It can do other things besides roughness, such as waviness. The skid system can only measure on a linear surface, a flat surface. If you had to measure on a non-linear surface like a radius for surface finish, that skid would deter you from following that surface and measuring. The skidless not only can physically follow a non-linear surface, but those systems will also have, either in the firmware or software, the ability to compensate or remove the overall geometry and give you roughness. And I have an example of that here in a moment. The only drawbacks to a skidless system. Oh boy, you're not going out there. There we go. The only drawbacks here is, since you don't have that skid and that high amount of force pressing against the surface, this is a little more susceptible to environmental issues such as vibration or even airflow. If there's a vent blowing directly on the sensor, that can impact at the resolution that we're measuring. So this is it's a rigid coupling, so you have the x-axis pulling only the detector, and the only movement is in that LVDT of that diamond following the peaks and valleys. So true representation of the surface, able to do many other things besides roughness. The only drawbacks is this system is a little bit larger. The drive unit itself is a little bit larger. It's a more expensive system, and it is a little more susceptible to things like vibration and environmental noise. So that's kind of the hardware, and that's a big thing to consider. There are definitely limitations with skidded. The styli only get so small, and some of the other things we talked about. The skidless has a much larger variety of probing or styli. They get smaller, deeper, longer with skidless. So that's a review of the hardware. Now this gets pretty technical, but it's very important to understand what's really going on when we take a measurement and how that finally gets you a number at the end, RA of 32 microinch or whatever it may be. It's not as simple as most of you have found. You don't just tell a system, measure a half an inch and give me an RA. There's a little more thought to it. There's some things that we have to consider of the surface that we expect. So we're going to get into some of those things. That chart shows there, right here. This is just how we need to measure with a tactile system. We need to make sure we are perpendicular to the lathe or measuring against the grain. We don't want to be going along in the valley. You'll just get a very low number. We need to go across and monitor those peaks and valleys. The attitude of the stylus, we need that normal to the surface, not tilted on an angle. We need that diamond on the end to be touching the surface and going up and down the valleys. Here's the fun stuff. So whenever we're looking for some type of surface texture, we're always applying two filters. We're going to eliminate things that are larger than we're looking for and smaller, even with roughness. So a good analogy is, and we'll do this in a moment, just we think of the frequencies in a surface. We have large ones, small ones. Let's talk about them like they're rocks and boulders and mountains. We need to isolate small things and get rid of big things. That LVDT is an analog sensor. So as that core moves up in the LVDT, it's changing the analog signal that's coming out. Well, we can't do much with that signal itself, so we need to convert it to digital information. So there's always going to be a filter that gets set, and I'm going to make your life easy. We almost exclusively use the Gaussian filter. There's some other older filters for older technologies. Now the Gaussian filter is used as your signal filter if you ever see that on any of your equipment. We're going to use a Gaussian filter that converts the analog signal to digital data points. That one we won't dwell on too much. Here's the fun stuff. How do we decide what to eliminate large and small? Well, it's all standardized, but let's start at the macro level, and whatever surface we're measuring, let's think as if we're out in space and looking at a mountain range. We can see everything. We can see the curvature of the earth, the really large peaks and valleys, and as we zoom in, we can see some of the other things. So that top picture, let's think of measuring surface finish on an arc like that and see how we get to the point where we isolate the roughness profile, because once we have the proper roughness profile, we can derive the roughness parameters that we're after. The very first thing that we have to do is eliminate any overall contour. If you're on a linear surface, there is no overall contour. We're just linear. But in this example, if we're measuring on a radius, the first thing we have to do is remove the radius. There are some other types of compensation, parabolic, elliptical, but they're very rarely used. It's usually when you're measuring on a radius, you use things like we see at the top, curve compensation. So if we turn that on a system, it will create a best fit circle and then take all those smaller components and straighten them out on a linear graph. So it's very important if you're not measuring on a linear surface, you need to make sure you compensate for the overall profile. There's the curve, and we take all the information along the curve and straighten it out on a linear profile. It's very important. Let's look at these three pictures. If I use my roughness tester and measure it on a curve, and I did not apply a compensation filter, I might get a number like 35 microinch, and there's some residual error still in there from the curve. If we had done it appropriately, we'd get the graph on the bottom, and it's a very different number of 15. So if your call out was 16 microinch and you didn't do this properly, you start failing parts because you're getting high numbers when in reality they were passing. There are things like tilt and inclination compensations as well. All right, now that we've removed any overall profile, what we have left is referred to as the P profile, or primary profile. That has all the different frequencies of surface texture. Now, we don't usually see these called out on a print. You don't see PA or PZ, but it's always in the software firmware, the start point. We have that surface texture information, the P profile, and typically we're going to start removing things to isolate the frequencies that we want. So you can think of that P profile as looking at that mountain range once we took the curvature of the Earth out. This is not as common as roughness, but another profile that is sometimes considered is called the Waviness Profile. It's the larger frequency components in the primary profile. If we want waviness, on the low end we remove roughness, get rid of all the small things, and on the high end we get rid of things larger than we're after with waviness, and that depends on the part. And as you can see from the previous slide, all that noise or smaller frequencies that were in the primary, we can remove those and have the larger frequencies and get waviness. That's commonly used on large area sealing surfaces where bigger frequencies may dissuade the mating part from sealing properly. But what we're usually after, and waviness would be like the larger ridges and removing boulders and rocks and things from our mountain range. This is kind of showing the types of filter we use, and we're going to start seeing these at the bottom here. I keep forgetting I have this guy here. The Greek letter lambda S, lambda C, lambda F. And we refer to these as cutoffs or filters, because what those are establishing, hey, these frequencies that are smaller, take them out, larger, take them out, and we've isolated what we want in the middle. This is the one that we're usually after. And in roughness, that middle character at the bottom, lambda C, many names, unfortunately. Sampling length, cutoff, lambda C. That is our low pass filter. So when we set a horizontal value like 30 thousandths of an inch is lambda C, what that means is any waveforms larger than 30 thousandths of an inch, remove them. And on the other end, on the left down there, we see the lambda S. That's our high pass filter. Filter out things that are smaller than this number. And we'll talk about that in a moment with roughness. Roughness, we can think about, we're trying to take out the larger components like the big ridges and isolate the smaller things. In this analogy, like boulders. Maybe we're walking across and we want to know how hard it's going to be. But there might be very small things that we also want to eliminate. In roughness, those small things are typically noise. It's frequencies created by electrical noise in the system itself, some noise in the environment, vibration to a degree, and some other things, but there can be this really high, small amplitude, high frequency components that we want to eliminate on the small end that are noise. We want to isolate roughness, so we take out the bigger things, waviness, and isolate roughness. So we can think of it as like mesh filters. If you're after a certain size rock, you can use one mesh to get rid of the little things, another mesh to get rid of the bigger things, and what you have left are the things in the middle that you're after. Luckily, we don't just arbitrarily decide I'm going to use certain values. This is all standardized, so when you see your print and it says check 16, that's assumed roughness, roughness average, RA, 16 microinch or less on our callout. Just that value tells us everything we need to know to properly set up this test. That chart there is in metric. When your callout in metric is in between 0.1 and 2 micron, 0.1 and 2 micron, you use a certain sampling length of 0.8. Most finishes that we measure fall in that range. In microinch, that's everything from above 4 microinch up to 80. So most of you, as you're doing your testing, you see 8 microinch RA, 16, 32, 63. Those all fall in that range. And the standard tells us we use a 30 thousandths of an inch cutoff, and that's what we typically use. As things get smoother, we use a smaller cutoff. As they get more rough, we use a larger. And that's that filter accepting and denying the different frequencies for what we're after. If you use the wrong cutoff, like the picture on the top, you may keep some of the things that you intended on eliminating, like waviness, and get an inappropriate result. So that lambda C, your sampling length cutoff, I'll probably say it 50 times. That is the most important thing because it's acting as a filter. If you use an inappropriate one, you are filtering inappropriately, and you're getting the wrong roughness profile, and you'll get all the incorrect results for the roughness profile. So it's the most critical, and it's the thing that, per the standard, you should use the appropriate one. That's one component of setting up a tactile roughness test, and it's the most important. So what else creates the overall length that we're measuring? Well, we usually want more than one of those cutoffs, 30 thou. The optimum number is 5. So if we set 30 thou cutoff times 5 samples, we are evaluating 150 thousandths of an inch. The yellow there is a feature that's on all of these systems called pre and post travel. It's extra distance you can add at the beginning and end that allows the motor to start pulling the system and ramp up, and then in the middle, at a consistent speed, take your test, and then at the end, the post, it gets to ramp down. So your measurement evaluation length in the middle is done at a consistent speed. That's just the same things here. So as I mentioned at the beginning, we don't walk up to the system and say, measure an inch and give me RA. We look at the expected RA, we define the appropriate sample length. We have X number of samples, 5 if we can, and we can turn pre and post travel on and off, and all of those things produce our traversing length, the actual physical length that it'll pull. Someone may say, what if I have a 16 finish, but the land I'm trying to measure is only 100 thou wide? Well, all those settings, 30 thou times 5, pre and post, that equals 180 thou. So what should I start manipulating first to reduce this length to measure on a smaller surface? Pre and post travel, first thing that you can eliminate. That's nice to have on, but first thing we take away if we need to. Then, if you still don't have enough room, start reducing the number of samples that you have. If it's 100 thou length, we would set our system to a 30 thou cutoff times 3. With no pre and post travel, now it's going to physically measure 90 thou on that 100 thou surface and give us our result. Aspect ratios, just when you're looking at a lot of these reports, they're greatly exaggerated in the vertical axis because if they weren't, everything would just look like a fairly flat line because the deviations up and down are so small. We greatly magnify them so you can see the peaks and valleys across there. I keep referring to a diamond stylus. These tactile systems, they have a diamond on the end, and those come in a variety of sizes and angles. That's all standardized as well. Most systems and most surfaces, you should be using a 2-micron radius diamond with a 60-degree angle, or a 5-micron with a 90-degree angle if you're on a rougher surface. We have information, charts and everything that can tell you, hey, your print calls out 16 micro-inch finish, you should be using this diamond, this setting, this setting, this setting. So that's the beauty of it, and a lot of the systems and software will have assistance right inside to help guide you. This is a pretty cool little test, theoretic test with different diamonds. If we think of especially the valleys, depending how narrow and deep they are, different sized diamonds can only get so far down. It's laid out a little better here. What this is showing is if you took a 5-micron radius diamond tip and tried to go down in the valley, if you had some kind of theoretic perfect 0 radius diamond, it would get all the way to the bottom. With a 2-micron radius tip, that would follow the surface and bottom out around here and get close to the bottom. But if you use too large of a diamond, it's going to slightly go in the valley and then come back out, and you're not going to get the depth that you expect. Here are 2 measurements overlaid on each other showing what if I measured here with a 2 and a 5? What kind of difference in result would I get? And you kind of see the blue and red here. The red is with 2-micron diamond, and it can get further down into valleys. The blue is the 5-micron, and it cannot. And the more correct representation of that real surface is the 2-micron, because it followed it further down. So that's kind of the hardware, and then the theory of all of the settings and the filters, and why did we just set all of that stuff up? It's so we could physically trace across the surface and use the appropriate filters and create the roughness profile, because all of the parameters that we're after are just using that profile and applying different calculations to it to report the numbers that we're after. So as long as you have the right settings and you're using the hardware the right way, you'll get the correct roughness profile. Once you have that, you can get all the answers that you want for 2D roughness. I'll mention a few other things here. Calibration of these systems is a little different than other things. They typically come with a 120 micro-inch RA reference specimen, the one at the top there, that has a very uniform sine wave type surface that is 120 micro-inch RA. We go through a calibration procedure with our system, and we say, we measure this, it's supposed to be 120, find out what it measured, and then use those 2 values to come up with a compensation value. Very important to calibrate these systems, but not too often, because every time you calibrate, you're changing that compensation. So I always suggest calibrate when necessary, when you're changing styli at some frequency, depending on how much you use it, but verify as often as you want. Now, what is the difference? In calibration, we're measuring, we're telling it it's supposed to be this, you got that, so come up with a value to adjust. Verification is just measuring that reference specimen and making sure it's as close to that 120 value as we expect it to. In our world, we get a lot of, we'll be the third party. Our customers say, my supplier measured this part and got this number, and I measured it and got a totally different number. You tell us who's right. Well, it depends. You can only start having that conversation if everything is duplicated. The settings are duplicated, the measuring speeds are duplicated, the hardware is the same. If I use a 2-micron diamond and you use a 5, we're going to get different results. So you need to duplicate everything, and then it can be a challenge to measure in the same place. I can move over just a little bit from where someone else measured and get a different reading. So marking the part and understanding where the measurements were taken, or taking multiple measurements and averaging them, can be a suggestion. But this can be hard to correlate. We're talking about millions of an inch. A micro-inch is a millionth of an inch. So any peak or valley different, or any defect in the surface, can cause radically different results. By the way, I sometimes get that question. If I'm checking my surface for RA and I see a big burr or scratch or something, and should I be measuring through there? No. This is not defect analysis. We want to measure what the process put that how that process created that surface. So we avoid any areas that are defects, and we want to see what that process is creating. So there's a lot to correlation between two different tactile systems because it can be difficult to measure in the same place. All right. We use the right hardware, we use the right filters and settings, and now we've created that roughness profile. It's just a bunch of data points. But it's the correct filtered roughness profile. I'd say more than 90% of users, they're only after one thing on that roughness profile, and it's capital R, small a, roughness average. But there are many, many useful other parameters, and they're grouped into families. I may go through these pretty quick and point out some important ones. But there are two averaging parameters. The one everyone's familiar with is RA. What that does is it calculates every single data point distance to the mean line in the center in every cutoff, and then averages them all together. So this is the most stable and consistent parameter. Since it's an average, it's the one we use to correlate and to calibrate. It's the one that's used mostly in the industry to check parts. Because it's an average, it's got a lot more consistency. There is another averaging parameter. Let's talk about it. RA. It's used a lot. It's very consistent, but there's one drawback to RA, and it's this. Those three surfaces look completely different, right? But they all have the same RA, 3 micron or 120 micron. Why is that? Because it's just an average. If you have like the bottom picture where it's a really fine surface with really deep valleys, that all gets averaged together and you get a 3. The top picture, you have this almost perfect sine wave uniform surface. It's also a 3. Those two surfaces are going to function differently with a mating part. And then you can have something like in the middle, and it's also a 3. So you can't really tell how uniform the surface is, how deep the valleys are, or anything of that nature with RA. So that's where a lot of these other ones, other parameters come into play. RQ is also averaging parameters, just different math. Used to be called RMS, the mean of squares. So that's an averaging parameter, but it weights the cutoffs a little bit heavier. But let's talk about some of these other very useful ones. Maybe 10 years ago, I would have said 99% of users only look for RA. But RZ is a very important parameter, and it's becoming more and more used, and probably eventually we'll see on most prints an RA and RZ cutoff, because RZ is almost the opposite of RA. We're looking for the extremes in each cutoff. So if we set this to 30 thou times 5 for our setting, it creates this roughness profile. But if this were our first cutoff, this first 30 thou right here, what RZ does is it finds the very highest point and very lowest and gives you that vertical distance. Repeats that in each cutoff, and then it takes those values and it averages them together. So it's the extreme peak to valley in each cutoff, and then average it together, so you're getting an average of the extremes across the surface. So that gives a lot more definition. If we measured those 3 different surfaces that looked different from each other, they would have radically different RZs where they had the same RA. RP. Sometimes in this type of test, we're more interested in the peaks. And maybe this is a sealing surface, and if a peak is too high, it won't seal properly, and we'll have an avenue for gas or liquid or whatever it is to escape. So there are parameters like RP, which are looking at the highest peaks in each cutoff or across the whole thing. Conversely, RV, roughness valley depth. If we're really interested in the valleys, RV can tell you a lot about how deep those valleys are across those surfaces. And then we get into some really specialty ones. RZ1 max will look in each cutoff and see what the peak to valley height is, and then report to you the one that had the biggest value. So it's like the extreme of the test that you took, at least in one cutoff. And then here's the most sensitive parameter. RT is called roughness total height. anywhere across my test, find the very highest, the very lowest, and tell me the total height of this roughness profile. So that's going to be the most sensitive. If I measure here and there's really no peaks, I'll get a low number. If I measure over here and there happens to be one really big peak, it's going to report that. So it's the most sensitive. And then there's a bunch of specialty parameters that have a lot of definition and can do some predicting. I can't even remember. I think there are about 80 roughness parameters throughout the different standards that you can use for different situations. Most of the time we're looking at the peaks and valleys because something is mating to the surface. Sometimes we want valleys to be deep enough to retain lubricant, like a piston in an engine, in a cylinder liner. If it's too smooth and it doesn't have valleys, it can't retain lubrication and it's going to get hot and seize up. If it's too rough, those two surfaces are going to degrade each other and damage. So we need something in the middle, a sweet spot. There's a whole world of parameters that can look at those profiles and do some predicting and estimation of lubricant retention, things of that nature. If it's a metal seal, we're probably looking at the peaks a lot, right? Because any protruding peak is not going to let it seal. But you'd be surprised some of the things that these parameters can help you identify. Some of them are useful for adhesion. The X distance spacing horizontally of peaks can impact how something will adhere to that surface. If you don't have enough peaks, maybe the paint won't stick to it. So there's a whole world of them on all these systems. What's nice is if you don't know what parameter really identifies for you what is a good and bad part, most of these systems you can just turn a lot of these parameters on, do some testing on good and bad parts, and figure out which parameter identifies what you're after. We don't want to talk about that stuff. That's what I just mentioned. Good example of surface finish. It's surprising. If you look at a vehicle, there are hundreds of different components that require some type of surface texture test, waviness, roughness, the different parameters to identify bearings that are carrying a load or how something is going to seal. There's so many uses for roughness or other surface testing, and it's not just vehicles. It's any critical component that especially is going to have a mating part and have some type of friction or anything like that. And then I like to show this because there's a whole standard about how to properly call out surface roughness on a print, and almost no one utilizes the right way. We just see a check mark with a number. There's a lot of assumptions there, and it's very common. So if we see a check mark with 16, we start assuming, well, we're after RA because you didn't specify any other parameter. 16 microinch RA upper limit. But there is a way to control many other things when doing a roughness test. And some of those advanced tests where you want to set a lower limit, an upper limit, maybe more than one parameter. You can identify if this test should be taken before or after a certain process. There's a whole science to properly calling out roughness that almost no one uses. The Germans like to, though. So yeah, if you see anything like this on a print, that's probably a more advanced test, and there's different areas in those boxes that they're placing different identifiers that will tell you how to set up your test. Luckily for everyone in this room, Productivity Quality has a lot of very knowledgeable staff that use these systems and can guide you through taking the correct tests. And then also, Mitutoyo has a lot of resources that we can provide as well. So that's 2D tactile roughness testing. If you get anything out of that, it's that cutoff. Look for that chart. Look at the number you're after. If you're making a really smooth part and it says the RA is 2 microinch, that means a lot. That tells you what sampling length to use, the number of samples. It's the most critical component because if you use the incorrect cutoff, you will get the incorrect roughness profile, therefore you will get incorrect results. So it's very, very important. Any questions? I'll hang out afterwards too if you have any questions for me, but I appreciate your time. And I'll hand it over to Adam to discuss non-contact surface testing. You want this thing?
All right, hi everybody, I'm Adam. I'll tab through this pretty quick, but I'll be around here after the presentation for questions, and we also have our Sensofar SNEOX out on display, so I can talk about it more later in detail with anybody who's interested. So our Sensofar SNEOX is our 3D optical profiler, so we're going to be looking at surface finish, form, and small geometric features, obviously without touching it optically. So what are we doing with this? We're going to be gathering a 3D point cloud. So we will be looking down on our object and we'll be able to measure X, Y, and Z space. We have a couple technologies to do this. So these are technologies common across the industry. Sensofar is unique where we have all three of these technologies in a single sensor head. So first we have a confocal technique. We have an interferometry technique, and we have a focus variation technique. Confocal and interferometry are going to be our surface finish techniques, and then focus variation is typically used for our form or geometric measurements. Confocal, we have the best lateral accuracy with that. So in X and Y space, we can define features down to 150 nanometers. With that, we still have fairly good resolution. So our vertical resolution there to define peaks and stuff can be down to single nanometer levels. Next, we have interferometry. This is our most accurate for vertical resolution. So we're going to be measuring glass, mirrors, very, very fine features with this because we can get sub-nanometer vertical resolution. Focus variation, like I said, we typically measure form with this. It's going to be less accurate in X and Y, just because we're kind of averaging and using the pixels around a single pixel to define what's in or out of focus, but it's very, very fast. So we're going to use this to cover large areas on a part. When I say large areas on the part, when we're using our microscope here, that's going to be a couple millimeters. It's not going to be inches long. We'll jump on to the next one here. So we have standards that define our parameters just like we do in tactile measurements. So we have an ISO standard that defines our aerial parameters, and you'll find that they are very common to our tactile ones, where we're looking for RA, RP, R parameters, or our roughness parameters. For aerial parameters, they're going to be S parameters, so over the surface area. So we're going to have SA, SP parameters in that liking, where we're defining equivalent math just in 3D space. So we'll step through all these, what the standard says, what surfaces we want to look at. So again, like Tony said, filtering is very important. We can look at very different surfaces and get very different numbers if we're not filtering properly. We'll kind of jump in and brief through what each of those parameters mean and how we can use those in 3D space. So we have a lot more information when we're looking at something in 3D space. So we can characterize parameters and kind of shapes and objects within our surface finish a little bit different than a tactile measurement. So the parts we cover here, we have our terms and definitions and what those particular parameters are. Like we talked about on technologies, Part 6 of this standard defines the technologies that this standard is applicable for. So we'll see we have interferometry there and confocal there. Those are the primary technologies for aerial surface finish. When we're measuring surface finish, we need to break down the proper surface. So we saw this with Tony in filtering. So in the middle here, we have what could be our pin, right? We have what we would assume to be a perfect circle, but if we look at it closer and closer, we know that there's more texture on this surface. So we might remove our perfect circular form and result in, let's see if this works, a profile here, where we have still multiple parameters within a single profile that we need to isolate down to our surface roughness or our waviness. Here we have a scan in 3D space. We typically view these scans on a color map like we see here. So our blues are our low points and our reds are our high points. So as we can see here, it's kind of a sphere or a sphere shape where the blue in the middle is low and all of our extreme positions in the corners are red. So from there, we want to remove our form. So we see our surface is getting flatter. We've removed a perfect sphere and kind of leveled everything out. But we can still see we have some blue low areas and some red high areas. So this still has our waviness in it in addition to our roughness. We can remove that waviness, and this is what we see here, where we see just the fine features that were visible on our spherical sample. So we can see them all here in space. Image on the far left, we can kind of visually see that texture, right? We can see there's visible scratches on it, but they're all the same color, so it's harder to isolate them in vertical space to characterize them as compared to the image on the right. Operators and filters. This one will be quick. Tony covered this. So we have different filter levels in our aerial parameters. These are S, L, F. But it's the same as the cutoff logic, where we need to apply a cutoff that isolates the surface we're interested in. When we're taking our scans in 3D, another important thing we do often is a thresholding filter. So just like we were filtering noise with a low or a high pass filter with our tactile system, our aerial scanner is susceptible to noise, and that's typically seen as very high peaks in our skin. So we're typically applying a threshold so we don't skew our peak parameters. We'll jump through a handful of the surface finish parameters. So we have what we see as typical R parameters, but again, they're just going to be S values here. So most common is going to be our SA and our SQs. These are our average values. This is what people see and use the most. We have our peak parameters as well. We're looking at values, we're looking at peaks. We could be looking at the total height in this area we're interested in. So the advantage here we see in 3D space is we're not doing a single profile line that's 100 thou long, but it's only 2 micrometers wide, right? That's the size of our diamond stylus. Now we have much more data to characterize what are the actual peaks on our sample in a much larger space. We have our averaging parameters, so SA and SQ. The most common we see, but like Tony said, they're very susceptible to not necessarily telling us a lot about our surfaces here. So again, we have 2 images where our blues represent our lows, our red represents our highs. It's the same image, but it's simply inverted. They result in the same SA value, but obviously these 2 surfaces will perform very different in whatever their mating application is. We have some correlation parameters here where we can say we see these geometries show up in 3D space. How often do they repeat themselves, and how close are these repetitions to each other? So this can be kind of drive performance in ceilings, or friction on the surface we're interested in. These hybrid parameters are very particular on the surfaces, but they look at how much area did we add to what would be a perfectly flat surface. So as we bring this texture into our part here, we're increasing the surface area of that part. So we can kind of quantify how much surface area we're bringing into this and how steep or what the slope is of this included texture. We have our functional parameters. So these are used in fluid retention, sealing surfaces. We want to hold some fluid within our surface. We have to be able to quantify that somehow. A couple of other parameters. So these are kind of feature characteristics of the part. We might not even measure the height of these characteristics, but there is a visible pattern to them. So we can kind of quantify that visible pattern that might not have an associated height difference with it. Contact versus non-contact. Tony got into this a little bit with the diamond stylus size with non-contact. It's not perfect, but our diamond size is theoretically zero with it, right? We can see further into the pits, and we also are less concerned with the texture direction. So when we measure with a contact stylus, we want to go perpendicular to our texture direction. As we see something in 3D space, we're independent of that texture direction. Here we can see our morphological filter, where we could simulate putting a diamond stylus across our profile and see the areas that we would not be able to measure with a contact system. How can we optimize these? What can they tell us? So there's tons and tons of parameters. As Tony said, with contact systems, there's 60 parameters across all of the standards. Most common we're seeing is RA. What does that really tell us about a surface? Not a lot, other than people know RA is surface finish. So we kind of need to iterate through the different parameters to help us isolate what two different functional surfaces do, right? We have a group of good parts, we have a group of bad parts. They're measuring the same RA. How can we quantify the differences in those? On the Sensofar system, we have a module for that. So we can scan good parts, we can scan bad parts. We can bring those into our analysis software, and it checks all of the parameters on all of the surfaces we bring in, and it helps us isolate parameters that are different between our two different surfaces. So it kind of stops our guessing game and says, we'll just do the math for all of the available parameters and say, these two surfaces vary on, in this case, an STR parameter, which looks at how much added surface is there because of my texture. So it kind of eliminates the guessing game of figuring out what the differences are between surfaces. Practical case, the same thing here with the included area. So this is for a solar cell, and basically they had 3 different processes, and this SDR parameter was the biggest differentiator between the surfaces, and they found that they needed some additional included area, but at a certain point when the SDR got too high and there was too much included area, they were losing performance actually in the ability to capture photons. So there was an optimal setting of included area somewhere in the middle between the multiple surfaces that resulted in the highest performance. So aerial parameters can help us see much more surface finish on a single acquisition and kind of allows us to better isolate parameters rather than just an average value that we typically see. So that's all I have. It was quick and brief. We have our Sensofar SNEOX out there. We have multiple Mitutoyo contact surface finish analyzers out there as well. Please stop by and see those. Does anybody have any questions? All right. Thanks for joining us. That's all we have today. We hope to see some of you guys out with us afterward.